Hello friends, welcome back to another installment in this series about the Raytracer challenge by James Buck, where I'm using the language Rust to implement a raytracer while I'm following along this book. A language, by the way, which I've never used before. This is the first project I'm writing in Rust. And so we are together going on a journey, experiencing all the learnings and the pitfalls of this language while doing this. You can easily find all the code we are writing and creating here in the description below this video, as well as more follow-up information to follow along. And now let's see where we stopped the last time. We are in the middle of chapter 4, I guess, or was it chapter 5 already? We are in the middle of chapter 5. And the last position where we stopped was we actually implemented a function or an implementation on a sphere which allows us to take a ray, which we implemented before, which we are shooting into the scene and through the three-dimensional world we are creating, and checking using this functionality here, which is a lot of math, if this ray intersects with the sphere, and if it does, where it does so. So that is what we actually did the last time. And as before, because then we can go further along quite quicker, I've implemented the tests from the book beforehand, so we can go ahead and take all those tests here. But as you can see, I've not done an implementation here yet. So these are only the tests, and I've not implemented anything further along because I want to do this with you in conjunction in these videos together with you. I want to learn this language. One thing I did, however, was to evaluate in a little example I checked, not with regards to the raytracer, but with what we are going to do there, how we can solve a certain problem we have to do now. So let me explain to you what we want to actually implement as a next step within our raytracer. So as you can see here on the left side, we have those intersections, and those intersection structs contain the value t. It's essentially a value which tells the system where a certain ray intersected with an object. However, currently it is like we only have one sphere we are intersecting with, but when we have a more complex scene later on, we will have multiple objects. They might not even be spheres, they might any other object, like there might be a rectangle, or they might be a plane or a triangular surface like a complex 3D model or something like that. We might implement that while going along, and so we need further information about those calculated intersections to be processed later on. Essentially, we need information about which object was hit by a ray and at which point. So we somehow need to store something here, like in my pre-evaluations and my tests, I called it body. So let's do this and call this one body here. I'm not 100% sure if I called it body or object. We will see. We need something here, some type, which essentially stores our body. And we could, of course, do something like this here. This would work. Then we would of course need to initialize this here properly, but we could easily do that. And while this intersection is calculated and we now get those intersection information here, we could easily put the sphere in there, the object which was intersected with, and everything would be okay. This would work out actually, not really currently, because then our sphere would need to implement certain traits, like for example copy and clone, to be put in there as a copy of the data struct. But this wouldn't be a problem. We could simply derive those and we could put this in there. There is a problem, however. As soon as we have another kind of object here, another kind of body, which is not a sphere, we would actually have the problem of where do we put it? Because if we now have a rectangle, which is another struct, it is another implementation, it has its own intersection function, it may have its own material information, transformations, which we need later on to process all of this. Where do we put this? Because we can only put a sphere in here, and the system would tell us, okay, you cannot put, for example, a rectangle in there if we have one at a certain point. So yeah, what we definitely could do, of course, is we could maybe move this intersection stuff, or the what we need in combined information. We could move this to a trait, for example, in order to have access to then, let's say, an intersectable trait. And then we could actually put objects in here which implement this trait. This is, however, not that easy. You cannot do something like this. I cannot do something like, for example, trait intersectable, which then would have this function intersect something. Yeah, let's just leave it at that. It's just a test. I cannot then tell the system I want an intersectable here. This will not work, and as the compiler tells us, a trait objects without an explicit dyn are deprecated. So what does this dyn mean? It means that we want a dynamically casted thing here. We could do it. That is actually a system the compiler can use to do this. We can actually put something like a dyn intersectable here, which means dynamic in this case. So the compiler knows that it can only at runtime determine which kind of type of object which is implementing this trait is it here. And so it creates all those vtable stuff in the background, like, for example, the C++ compiler does as well when using virtual functions and stuff like that. So then it can at runtime decide if you call the, for example, intersect method then on such a dyn object. It can decide at runtime during a second indirection which kind of intersectable implementation it needs to call now. So this actually works. I've played around with it a little, and it is not perfect for what we need to do here. Essentially, you can do this. However, it is. I did some benchmarks, and our raytracer will not be optimized at all. So this won't be much of a concern, but this is of course slower than a direct call because there is this second indirection. But furthermore, we need to then take account of this intersectable, and we cannot easily determine, at least I didn't find a way to easily determine later on what kind of object this is. This might not even be needed at all, but it is harder to operate with this thing. So I came across during my research another technique which we could use that is called something like Enum Disptach or enumerated dispatch or something like that, which essentially allows the compiler to create those dispatching information during compile time. And it's a little bit trickier to do. It's not a lot work, but it's something which isn't that flexible. You could, for example, you need beforehand the information on which types actually implement this trait. With this dyn intersectable, if we were writing a library, for example, somebody on the outside could implement something which implements the trait intersectable and could just give it to our library, and it would work, and we could process it, and everything would work out as expected. So This is a plus, of course, but we are writing an integrated system. We are not writing a library which will be used by other people later on, which might implement further objects to intersect with. If someone would implement further objects for our world with intersection functions, they would implement this within our code base. So there shouldn't be a problem to know beforehand which types we have. And it is actually a little bit easier to follow along if we know it beforehand. So let's check how we could do this. Actually, we are creating something like an Enum struct, which we call, for example, body. And this body Enum struct here has then corresponding entries for our different, no, I guess we define it like this, for our different types. So if we would have a rectangle here, for example, we could define this one here as well. And we define all those types here within our enumeration with clear typings so that the compiler can check against this. For now we only have the sphere, but we will see. So now we have this here, and we can actually then, I guess, tell this one. So we now tell this body enumeration that it implements intersectable for body. We now tell this one that we need to implement this trait here, which our sphere will implement later on. We will do that in a second. Sorry, as well. So yeah, let's check if we can do this. And what we are then implementing there, we will see in a second. So first of all, let's now fix our intersect information here, which now needs really to be the correct function, because now we are doing it. So the function stays the same. It always takes a self, it takes array, and it simply returns a bunch of intersection informations. So now that we have this one, we now have our enumeration here, so we can fix up this type and really say, okay, we are storing a body here. Simply one of those enumeration types we defined here before. So what we can do now is we can store there a body with the enumeration type sphere. We could, if we have a rectangle, we could then store a body in here as well, which has this enumeration type, but we know it beforehand. So we now have actually built our structure, which can collect all those different types within here. So what we are doing now is we are implementing the intersectable trait for body itself. So what we are going to do here is have this function edit here. Okay, so now I need to, I guess I need to fix up some of those imports here, because the IDE always uses the full import. If I'm doing this, I need to check if I can configure this somewhere. So now I can go here and can implement this. But how would I implement this? It's no problem at all. I'm doing a match actually then on the, we have a reference here, but we want to match on the object itself, on the real one. So we are dereferencing it here. And so now I can do a match, and I can match against this one and tell it, okay, what if it's a sphere type? If it's a sphere type, give me a reference to this sphere. And by the way, this is a new keyword I had to learn about. The problem here is the following. If I would be doing this, if I'm saying I want a reference here to a sphere, it could not match, because the match is always checking against the the real value here it gets. So what I need to tell, and as I'm putting a real sphere in here, a value sphere and not a reference, it wouldn't be able to match this. But what I want is, I do not want it to copy the sphere out of here again. I just want it to give us a reference. So inside of Enum matches, there is this special identifier ref, which we can use to get a reference to this sphere inside of this enumeration, because for this step we don't want to copy it anymore. It's just an optimization. We could leave this out here and it would work fine as well, but why not optimize this? So what I'm doing now here is, as I know that our sphere is going to, we haven't done that yet, is going to implement this intersectable trait as well, I can actually call this intersect here on the sphere and tell it to actually intersect with the same ray, and we are returning the result. So what we are essentially doing here is, we are dispatching here statically if the body type we have, because we are implementing this on body and matching against this thing itself, is a sphere, we want to dispatch to the sphere. So what we are essentially doing is, we are creating our kind of vtable, you could say. So we are creating our dispatch table there, but in code, so that the compiler can know at compile time where to dispatch stuff. This isn't as flexible, as I've said, as the dynamic dispatching, but for our use case, it's completely sufficient. So once we have implemented this one, what is it complaining about here? Expected tuple struct or tuple variant found. We need to fully specify this here. So we need to put there the body double colon sphere, and now as you can see it works. So what now works out is that this body here, you can call intersect on any body and it will dispatch to the correct type within this body. So we could use body as a wrapper around our sphere or rectangle or model or whatever we are going to implement later on, and it will always know how to call the correct intersect method. And once we are adding a rectangle here, for example in the body enumeration, we simply add an intersect match and dispatch rule here as well, for example for the rectangle. If we are going to implement another method we are going to need later on maybe, which needs to be present on all of those bodies, we could easily implement this here as well, and then dispatch it exactly like this. There is actually a crate in Rust which is called Enum Disptach, and it does exactly that within a macro. So if I'm going to check it out, we won't most likely not be using it, because I want to have it explicit for now to understand it by myself what it is doing. But essentially this Enum Disptach crate explains or does exactly the same thing. So it has some kind of trait here. This would be our intersectable trait. It defines some functions here. Then it has different structs, which, for example, in this case, a linear knob and a logarithmic knob, that would be something like our sphere or rectangle or whatever we want there. And then it implements those this trait for both of those knobs here, the linear knob and the logarithmic knob. My God, that's kind of hard to pronounce. It implements this one here for both of those, and then it could do that's what I explained. And as you can see, it then quite easily gets ugly, because you might need to, in comparison with the dun object, you might need to box it as well, to store it on the heap and stuff like that, and it gets ugly quite fast. But the solution to this is exactly what we did here. We have this enumeration which encapsulates this structures here. That's exactly what we did now with our body enumeration. And then you have the enumeration implement the trait as well and simply dispatch to the here, let's say, to the correct functions within the known implementation. And that's exactly what we have done so far. But as you can see, this this macro we have here, or I'm not 100% sure if it's still a macro or something else, but this crate, which we could install, we could simply then specify something like we want to use this Enum Disptach on our trait, and then we would essentially tell our enumeration specifically that we want to dispatch based on this trait. And this would be everything we need to do. And the crate would automatically, during compile time, create all those matching code here, which then dispatches for every of the implemented functions to the correct implementation. But essentially, as this does in the background nothing else than what we have just done, I guess I will for now stay with explicitly implementing it. Maybe we will refactor it later on to use this when we get a lot more methods. I'm not yet sure how many methods we will need to implement on this in the future. So let's see if it gets if it's not easily readable in the future. We will simply change to maybe this macro. But as you can see, it is there, and I found this quite interesting. And it seems to me that for all of my reading up, that this technique here, no, sorry, not this technique. This technique here, the one that we use, is essentially, it is not a bad practice or something like that in Rust. It is the way to do it because it is more performant and more easily handleable. It can be easier handled than the dynamic dispatching stuff, in case you know all the different implementations beforehand. If you are implementing a library which needs to handle different implementation things there later on which you don't know beforehand, you can only do dynamic dispatch. But if you know it beforehand, this Enum dispatching pattern is not a bad thing and is quite often used. So I guess we will use it as well. So now let's get back to our code and let's implement this. So now we have this intersectable here. We have our body, which currently is only a sphere. We have already implemented intersectable for our body, which then calls this intersect on sphere, but sphere does not yet implement, is not guaranteed to implement the same thing than this trait. And for this, in order for this to really work out, we would need to do this. Of course, this works now because our sphere simply implements an intersect function with exactly the same struct here, the same parameters and method signature than the intersectable. But to guarantee this, I guess we simply want to move this here out of the sphere implementation itself and put it into an implement intersectable for sphere. And now we are sure that it is really available there and that we can dispatch to it. So of course our intersection still is missing this body field. So I guess we will simply edit here, body, which will then be a body. And then we have a body here. And now let me quickly check up with actually with my tests if I really called it body. I know I called the enumeration body, but how did I call the do I even have those tests in here? Because I'm not 100% sure how I called this property here, if it's called body, or because the book talks about objects all the time. But I've played around in my head with if I should call this enumeration object, but I thought this would be too ambiguous. So body is more of a mathematical term. It's a 3D body. It's there. It can be described. It's a term that fits the description. So we could have called it world object, but I didn't want to call it world object or something like that. So I guess we are stuck with body. But let me just check how I did this there. Let me go into the Raytracer challenge prepare, and there we are. So let's see, I've got structured it here. I guess I've put it in the intersections RS, I guess. There are the tests we are currently looking for. So let's see, did I or did I not? No, it's not in there. So where is it actually? So where did we put this? Maybe we put it in Ray? No, I don't believe well, maybe we did. Or maybe I did, better said. Because I wrote the tests up front. Let's check. Do we have creating a querying array, computing a point from a distance, translating array, scaling array? No. So it's not within the ray tests. So maybe it's not here, but where do we actually, maybe it is in the sphere tests after all. Wait a second, let's check. Array misses a sphere, origin is inside a sphere is behind array. That are all tests that we have implemented there. An intersection encapsulates T and an object. And let's check, we are checking body. Yeah, we called it body. So I'm right here about assuming that it's called body. So yeah, let's go along and do it this way. So for now, one thing has actually to change here. We now cannot implement those or return those intersections here in our intersectable for sphere. What has happened here with the... do you see this? This is the wrong color. The syntax highlighting kind of is broken there. Okay, we are not looking too hard at this. So we now of course need to add this object here, and the question here is now, how do we create our body object? Because what I cannot do here now is I cannot just put in our sphere. I cannot just do something like self here. So the compiler then tells us mismatch types. Come on. Or let me hover this so we can see it. It tells us mismatch types. It is expecting an enum sphere body, but found a reference to a sphere. So we have two different problems here actually. The first one is that we are expecting something from this enum type. We can fix this easily by simply putting a body in front. We are knowing at this point we are inside a sphere, so we can just wrap it inside this enumeration and tell the system, okay, create a new enum and put this one in there. But now we have another problem. We have the problem that that it founds a reference to a sphere, but it wants actually a real sphere. So it is of course here like the self is a reference, you can see it here, but we want the real deal. So what we can do here is of course we can dereference it and put it in there. This should actually work. I'm not 100% sure why this works. I guess if I do it this way, the next one here will not work anymore. Let's check this, because until now we have not implemented the fact that the sphere is copyable or clonable. So let's check if this is working or if the compiler is then crying out. There. It tells us exactly that. Cannot move out of self, which is behind a shared reference. So essentially what we have told the compiler here is to give up the its own reference here to self, to this object of the sphere, and put it inside this body object, because it cannot easily copy it. It could only transfer over the ownership now to this enumeration and therefore into this intersection. But we can easily fix this by, we could put a reference in there, but the problem with the reference is that then the compiler would need to know how long this reference lives, and we would have a lot of cross-dependent referencing lifetime problem stuff there. And essentially a sphere is not a big construct in memory, so we could easily, where is our sphere struct, we could easily allow the compiler to just, let's derive copy, oh no, it's need to be copy and clone. And now, yeah, can't leak private type. What has happened here? Maybe this is not private type, sphere body in public interface, private type, sphere body. Did I? Yeah, I missed to put a public before the enumeration, and now everything should be good. Okay, what I essentially did here now is I allowed the compiler to copy sphere structs. So if it encounters this one, it doesn't need to move ownership. It can simply bit copy all the data from the sphere into the new structure it needs and put it in there. So it will essentially do something like a mem copy there in the background. I'm not 100% sure. The compiler might even optimize this away by inlining functions and stuff, but I don't really care about this at this moment. It should be fast enough. As I've said, we are not yet trying to optimize this in an absolute manner regarding the raytracer, because we just want it to run. We can maybe start optimizing it once we have finished this series and implemented all the stuff we want implementing. But before that, we just want to implement it in a working way. And this is the easiest way. And I'm not even 100% sure if doing something like complex referencing or using those heap allocations, which we most likely would need then to allocate those objects on the heap and then referencing the heap there instead of using the stack, which can be done in Rust, of course, as well, would even be faster or work better than just having the compiler trying to optimize it away and copying the data if it needs to. So we can do this here, but this is not really nice in kind of a way. So we can do this, but it looks a little bit ugly. And furthermore, if we have somewhere some object, we would always need to call the proper enumeration type. So what we can do to make this even nicer is we can implement on our body. Let's implement from was it how would we implement this? I mean this was done here as well, I guess. Yeah, what we want to be able to do later on is essentially to do this here, to have something like we want to call just from, put one of those different types like a sphere or a rectangle or something like that inside there, and then inside of the enum a matching takes place, and it would essentially then handle all of this for us correctly. So that would essentially be what I would like to implement. And there is this from trait which would be implemented for, yeah, I guess we then need to, yeah, of course, we need to implement it for every type we have. So we are implementing the from within this one, yes, I guess. So we are implementing the from trait for the type sphere. So if we are coming from a sphere and we want a body, we would then implement exactly this from function here, which then would mean that we have our sphere here and we need to return a body, and this would simply then return, I guess, a sphere and put the sphere in there. So, oh yes, we of course need this. Do we need this? No, we don't. We don't need this. We actually know this is a sphere. It's not a type T. Yeah. Because we are not implementing a generic version. We could, maybe we could, with some matching, create a generic version, but I don't care really. We can simply implement it for all of the different types. So what I now can do here is, after I've implemented that, I can essentially, and I could even do some more. I could essentially, if I would like to, I could essentially, maybe we will see, implement it something like this as well and tell it to just dereference it then, so that we don't really need to take care about the dereferencing beforehand. Let's see. It would do it automatically then. It can do it because it can copy the stuff. And so let's see. I should be able to do from self here now, and it should actually work. Yeah, and as you can see, this is working out quite nicely. So it works. And let me check something else, because in Rust, if you are implementing the from trait, you are automatically implementing the, I guess, into trait as well. This is done by the Rust compiler in the background. So I should be able to do something like this here as well. Yes. So now the Rust compiler checks, okay, there needs to be, I need to put a body object in there, and it then checks, okay, there is a conversion which is implemented now from a reference of a sphere to, where did we implement it? There. A reference of sphere into a body, and it's here. And if I now tell it to just convert this reference of sphere into the proper value for this slot here, it will do it. But I essentially like, ooh, what did I do now? Yeah, then my undo didn't work and did some strange stuff. So I like the explicit one here better, and I'm not even sure if I would like it better like this too. Yeah, I guess I like it better like this. Let's remove this implementation again, because then it is explicit to the user of this one that we need a real value here to be put into the body and not a reference. Where is, so yeah, we have now this one. So let's check if we have any other test which needs handling here, but the tests don't even assume that. They are just working with that. So we are now creating those intersections. So now let's check if all our sphere tests are still running. So yeah, it needs to compile. Oh yeah, it seems to me we did a lot of, what did we do there? Oh, I'm in the, of course it cannot compile all this. I have a lot. I'm still in the preparation directory where all those tests are lying, but no implementation for them. So of course it is hardly crashing. And as you have, that's why it compiled so long and so much. I've never actually, of course, compiled this preparation directory, because I knew it wouldn't even compile or work, because there are tests but no implementation. So let's do the same thing in the right directory. Yeah, and now our unit tests are still passing, and this is really great. We refactored this thing to have a storage of those self references within our intersection objects now. And yeah, I guess we could, maybe we should refactor this into its own directory, file then, like maybe we should refactor then this intersectable trait and this body out somewhere. Yeah, I guess we could create a new file called maybe body rs, and oh no, it needs to be written lowercase, doesn't it? Body. So maybe let's put. We will see how many files we need for this, but I guess for now we could take all of this intersection related generic stuff like the trait and the body enumeration itself and the intersection. Actually, we could put all this here. So let's tell the compiler where it can find it, or at least that it should compile it. Now it should cry out because it doesn't know where all those types are coming from. Why is it crying out here? Yeah, cannot find intersectable. Of course not, because we now need to implement this one, but let's just implement all of those. Let's remove this because it seems to me we do not need this anymore. Yeah. So now, of course, this trait needs to be public. And then we would need to, I guess, use create, what is it? Ray and sphere. And yeah, there's definitely something wrong with my syntax highlighting here, and maybe use create f. So let me just quickly close this one and open it up again, because there's something wrong with the syntax highlighting. What is happening here? Cannot find sphere in this scope. I did something wrong here, didn't I? What did I do wrong here? So is this important that does it need to be the right definition order here somehow? No. Intersectable is not found, but I should have imported it. Pub trait intersectable, cannot find type sphere. Yeah, but I guess I've loaded it up here. Cannot find ray in this scope. Oh, there is a colon missing. Is this the problem, maybe? So now it does complain that it cannot find ray. Why is it complaining? Okay, let me just restart my IDE, because there's something strange going on there. I guess the language server just kind of crashed and gave us wrong information. So yeah, now it seems to me that this is working again. So I guess we have now moved it there, but let's check by simply running the tests again. Cargo test. Yeah, let's run all of them just to be sure. And yeah, they are still all passing. So yeah, seems to work as expected. Okay. So now actually, after we have extracted this, we are quite a bit further along with this implementation. The next thing we want to do is actually be able to, let me check. Yeah, let's maybe get the tests here, which assure that we are actually storing this object. So we have actually a test here which says an intersection encapsulates T and an object. So I guess we would move this then to, yeah, maybe then into the in here into the body thingy here. So of course we need this test harness around it definition style thingy. Let's copy this over. No, we wouldn't need all those. Let's check. So let's copy this. Let's remove all this. Let's put something there and let's check. This should actually work already. Let's see. So cargo test. No, it does not. Body cannot be formatted using. Oh, I see. So yeah, that's another thing. In order to use assert equals, the system actually does the following. It goes along and uses the debug formatting to format out the object to create a string representation of it, of both sides, and then simply compares them. So, but as our body cannot do this, we need to derive this one here. So we need to derive debug here, but I guess this will not work out because sphere doesn't implement debug as well, so it couldn't print out this one. So let's derive this one there as well, and now this should, okay, it does not. Cannot be applied to type body binary operation. Okay, that's kind of strange. Why not? There, an implementation of partial equality might be missing. So, oh, I see. So, it needs the debug one for printing out. It really does partial equality here. So, yeah, I guess let's define partial equality for the sphere then. So, a matrix does not have partial equality. Yeah, but I guess we could easily add this one, can't we? It's just an array, so it should be derivable there. Yeah, so a matrix can now be partially equal compared, and then we need a partial equality trait on this body thing, which now should be able to be derived. And let's check. Method not found in reference to F64. That's something to do with fuzzy equality. Why doesn't this work? We have implemented fuzzy equality quite some time ago. I'm not 100% sure how. We have implemented fuzzy equality and it's complaining about this one, which takes a reference to self and other t. And essentially what it is telling us here is that it, but I guess we haven't we implemented it for, yeah, we have implemented it for an F64. So, but it is telling it that it is not, okay, it's not implemented for the reference to an F64. Where is a reference to an F64 called? Essentially here, it seems to me. Why is this T a reference to an F64? Why isn't it just the F64? What is happening there? So it says that this one is a reference to an F64. So our intersection, okay, maybe we need to derive copy and clone for this one as well, and we can derive debug and partial equality as well. Yeah, maybe we don't need this. Let's only derive this if we need it. Let's derive at least copy and clone and debug for it as well, and let's see if this works out then. I guess it cannot. It can has a reference to an F64 because it has only a reference to the intersection here, maybe. So does this new return? No. That's, I find this kind of strange. Let's check what happens now. Okay, so it tells us that copy may not be implemented for this type. This field does not implement copy. So, but But didn't we just derive? Oh no, we did not. So maybe that's the problem here then. I guess the body can be copied. Why shouldn't it? The sphere can be copied, and our body, our body objects in there are the only thing in there. And as long as we allow copying for them, it should work. But this does not work anyways. So okay, let's remove this again, because I don't want to derive stuff there which we don't need. So, oh, what have I done now? I've removed more than I... Okay, that's this undo thing again. It seems to doesn't work out. So what have we just... We have told that there is a possibility of copy and clone the body. We don't want that anymore, or at least we don't need that anymore. And we don't need this for intersection. Yeah, but the debug thing I want to keep, just to be able to print it out, I guess. So now it should have only one error again, and it is this one. And I don't really get why this is a reference. Yeah, why this T here is actually a reference. So okay, let's try and find out what is going on here, because I don't really understand this one. So maybe let's comment out this macro here and call it by hand, just to make sure that if I have this intersection and I have this T value on it, I should be able to call fuzzy not equal function there, and I should be able to compare it with just some float. So let's call this and let's check if the test now crashes during compiling. Okay, it is not working out. No method named fuzzy ne found for type f64 in the current scope. Wait a second. The method is available for f64 here. So it tells us, so T is, I have a I guess our macro does something strange here. I guess it is because we have not used it here. Let's get this fuzzy equality trait in here, and let's check then if this works. Yes. Okay, that was the problem. Wait a second. Oh, we don't need it. We don't need it here. We need it here. So let's put it there, and then the warning should be gone as well. Yeah, it is. So what essentially was the problem? The problem was that we are implementing in this fuzzy equality thingy here, in this file, in this module, we are implementing this we implement this fuzzy equality checking for f64s, and we simply did not. Where were we? Body rs. Haven't I renamed this file? Okay, strange. We just haven't included this fuzzy equality here, so it didn't know how to fuzzy equal compare those two floating points. And the error message is kind of strange when we are using the, where is it? The macro. Then it tells us that the method cannot be found in a reference to an f64, and this is what threw me off. Essentially, that's where I thought something strange was going on. But once I really did it the manual way, it then confirmed to me that it isn't a reference and that fuzzy NE is not found in the current scope. And those gave me the idea that we need to actually import this. Okay, so now we are ensuring that we have encapsulated the body object here, which is quite nice. So the next thing we would like to do is to implement something on our intersections. So what we have here is once, where is it? once we have called this intersect, we are currently returning a vector of intersections. And the problem here is that those are quite a lot. And what we need essentially is we need the first of them. So we want to know where the first intersection with our object is. Because that is the one that is most important for us in order to render something, because we are firing rays into the scene, and we need to know which object they hit first. If they hit multiple objects, for example, we want to know if they we want to know the first one it hit. If we are hitting the sphere on the front side and the back side, we of course want to know the front side and not the back side, because we are not rendering the back side but the front side. So we always want to know the first hit. So we want some kind of convenience function there. Oops, sorry. What? Yeah. We want some sort of convenience function there, which actually would be able to give us this information. And we want to call this function hit, we want to be able to call on this collection of intersections. We want to call the hit function, and it gives us the first hit in its collection. So you might ask yourself, why are we storing all of those intersections then? We could always just return the first one. And for quite some time during the further implementation in this book, we will always only care about the first one. But the book tells us as well that once, and this makes absolute sense, once we get to a point where we want to calculate reflections, or we want to calculate, for example, semi-transparent objects like some sort of, for example, glass, or simply something which isn't completely opaque, or further different calculations we are going to make, we essentially need this information of further ray intersections down the road, because we may need multiple intersection information to calculate the final color of the pixel we want to render there. So as it is passing through objects and stuff like that. So we are for now just always putting in all those intersections, but we want a convenience function to return only the first one. So we could easily implement this, but where would we implement it? It seems to me that we now need to replace this vector here with something else, which is called intersections, or however, intersection collection or something like that. I guess we would need a data structure which can hold this. And the problem with that is that I want it to work exactly as we have it before, because I actually want to be able to access all of those different intersections here just using this array syntax. I like that. I want this information about length and stuff like that. So I guess we need to find a way to implement such a collection while still maintaining this behavior. And I guess we can do it mostly the same way we did with the matrix. We have this struct matrix here, which inside of it is has simply a data property which holds our internal data structure, which is an array. And then we implemented all of these traits here, like, where is it? Index and index mut and something like this to access the data using this array index stuff. And I guess we just need to find out what kind of traits we need to implement to have this len, and to have all this information. I'm guessing this is some sort of trait that the vector is implementing, so I guess we need to check this out. So yeah, maybe we are going to create a new file here, or are we putting this in a new file, or are we putting this in this body thing, as we have this intersectable trait there and this intersection. But maybe we want to split out this intersection information here and put this inside its own file together with the collection we are going to use. Yeah, let's think about this for a second. Yeah, I guess that's for now. Let me just put an intersections rs file here, and then let's put in there the intersections collection for now, and then we will worry about maybe moving the other stuff in there as well or not. Let's just see. Okay, so let's start implementing this intersections collection then. I guess we are, no, not in, we are creating it as a struct as before. We are calling it intersections, I guess. And it will hold as with the matrix, mostly identical, something like a private data property, I guess. And this private data property most likely will then be a vector of intersections, of intersection structs, I guess. As we don't know how many we are going to store there. Yeah, I think this is almost it, but let's include it here as well, so that that our system compiles it, so that we see errors up front, something like the semicolon I added there, which shouldn't be there actually, so let's remove that. Okay, yeah, of course it cannot find the type intersection. We need to include this, and let's simply include this whole module here. Let's make this struct public, I guess, and yeah, then we will start implementing it for now by creating a new function for it, I guess, and maybe implementing a from, yeah. So let's first implement wait a second, let's first implement, yeah, intersections. So we need our pub fn new, and we want to, yeah, how are we going to, we could just, yeah, I guess we are just putting in here maybe an array slice, or no, most likely a vector directly, aren't we? Yeah, I guess we are just putting in here we are just putting in here a vector, intersections, which is a vec of intersection objects. So we can put in exactly what we created before, and we return a self, I guess. And so then we would, yeah. Can we simply do then something like intersections, data intersections? Does this work? Field is never read, yeah, but it seems to work here. So we can put this in here, but then we will transfer ownership of this in here. But I guess this is okay. Yeah, I guess this is okay for now. So I guess we could implement, it would make sense to simply implement this from vec of intersection trait as well for intersections, so that we, wait a second, did I do this correctly here? Yeah, okay, so let's implement this one. This is this is the vector. Let's just call it v. It's a vec of intersections. No, intersection. Maybe the naming isn't this great. But yeah, so, and now we simply could return like something like actually self and call new on it with a v in there, and we would, this should work. Yeah, okay, so this is just for having a little bit easier life later on using it, I guess. So okay, so now that we have this one, I guess we need to implement the, what it was called index, but what was its signature directly? Let's check in the matrix. Index, it's simply index with an indexing type, and then we need to implement this. Yeah, okay, it's easy enough, I guess. So do we need to, sorry, do we need to implement this or import this? Okay, imp index with a usize, I guess, then for intersections. And now it should complain that, yeah, exactly, that we should import this this trait there, and then we need to, why I'm always getting the shortcut for making the text smaller. So yeah, of course, we need to specify output, which would be self, I guess. In this case, because, no, it will be, sorry, it will be an intersection. So if you address this, you are getting back one of the elements, and I guess then we need to implement this function here, which would be, this is the index, which would be index, and it's not IDX, it's usize in our case, and it will return, I have no idea what this will actually, it will, I guess it will return self output then. And okay, what is this? Method index has an incompatible type for trait expected body intersection, but found. Okay, so it actually expects a reference. Yeah, but this is fine for us. So then we could simply do self data index, I guess. Mismatched types. Okay, so we need to do it like this to return the reference. Yeah, okay, so we return the reference there. So now we should be able to index those intersections. I guess what is now missing, so this part should already work now if we would return intersections there, but this part won't, I guess. So let's check out if there is a trait which handles this array-like stuff. If there is no trait, let's just implement those, I guess. No, I don't want to find anything. I want to copy in the thing I just copied out the web page. So yeah, I guess then we could just return self.data.len, because we know this vector has something like this. Okay, that is quite easy. And let's do an is empty self, which returns a boolean as well, and it returns an is empty then, I guess. Let's not search. Let's format this. Okay, it's formatted. So essentially now, if we go ahead and let's see if we take this sphere implementation, and it does not implement, or it does not return now vec intersections, but it returns intersections. So our data struct, okay, of course it cannot, no, it cannot find it because we need to include it. Use create intersections, I guess. So Method intersect has an incompatible type for trait express. Yeah, of course, we need to adapt the trait. Where is the trait? I guess it was in the body file here. Intersectable, yes, and this one should return now intersections as well. We need to, of course, use create intersections there as well then. So let's format this. Okay, I see. So this one should now be intersections here as well. Okay, so now let's get back to sphere, and now method intersect is an incompatible type for trait expected. Wait a second. Didn't I just change this? I just changed this. So maybe the compiler isn't... Did it somewhat crash again already? Let me just check. Visual Studio Code. Let me start this one again because there's something strange. So yeah, now this works, but why does this work? Oh, because we implemented a from and it's automatically converting this then? That would be actually quite nice. But I'm not sure if I would like to do this. Okay, let's just check if our tests are still running, I guess. Cargo test. So no, they are not. So let's check why. Expected struct intersections found. Yeah, that's exactly, but not in where? In sphere line. Yeah, okay, but why isn't this marked by my IDE then? What's happening there? Because this one is red here. What is happening here? Binary cannot be applied to type sphere. Note an implementation of partial equality might be missing for sphere. Didn't we change this? What is happening here? Sphere is not partially. Wait a second, is there something else wrong with this? Strange. Okay. Yeah, it is. What happens if I do this? So then this works, but if I just put it there, it doesn't know that it's not returning the right type. That's kind of strange. I guess I could do an into here now because we have this type. Let's just check this. Expected struct intersections found struct. Okay, so where is this actually happening? Oh, it's okay. It's this empty thingy here. So the into actually works because we implemented the from. Oh, the from trait. Okay, so our refactoring to have a struct called intersections, which now holds our vector, has worked out quite nicely. But I guess maybe we want to. I guess maybe we want to do it. I actually like this more explicit form to say created from this information, because I guess then it's easier for me to directly see what we are actually creating there. And yeah, I guess as we have this new function anyway, I would like this more than the from actually. Maybe I'm not 100% sure, but as we are using this one at all the other locations anyway, I guess we can do it here as well. So yeah, let's check, but I guess our tests will run. Okay, so our tests are running, that's nice. So as we have refactored this one now, I guess we can check what kind of tests, if any, I wrote for the Raytracer challenge prepared source. Did I call it intersections? I called it intersections, so that's nice. Yeah, that's a hit test, So yeah, so now let's actually, that's quite interesting, because now we can copy over all those tests here. Let's close this again and let's put this in here. And let's see, yeah, those tests now, which I've just copied over, are the ones the book describes. to implement this, this hit function I've talked about before. This hit function is assumed to take, for example, the hit function when all intersections has a positive t. It should return the first intersection, the one which is nearest to our origin point, which has the lowest t, which is greater than 0 actually. So this is the same thing here as well, but if some intersection is negative, in this case we want the first positive one. So that if we have for example, we had this case where we were starting in the middle of our sphere, something like that, and then we would have a negative t which is outside and a positive t which is going forward, and then we want, of course, the forward hit. We want the first hit starting from our origin actually. So this would be then the first positive hit. And if both are negative, what should we return then? Then we should obviously return no hits, because in front of our array there is no hit anymore. Okay, so if this is the logic of our hit function, I guess we can simply implement this one. Yeah, so I guess let's implement this one. It's a public fn hit. It gets no parameters and it returns then an optional, because we may return some value here, or we may return none value here. We've seen this optional thingy before. What's kind of interesting is now that I know that this exists, I'm obviously using it more. I guess this wasn't optional, it was option, I guess, and the return value here would be an intersection. So we are getting an optional intersection here. So yeah, so I guess we can implement this by, yeah, I guess we first need to somehow sort our data by the t, and then we could extract the needed value just by, yeah. Question here is, do we want to sort again for each hit call, or do we want to simply do this once this thing is created? So we could actually sort all this stuff once when an intersection collection is created, because I guess we will call hit more than once on it. I have no idea. Let me check where actually the book does or how the book defines it. Is there any sorting defined, or is it just telling us to kind of return just the correct thingy matching those tests? So let's see. There is this collection identifying hits. There it is. It is just defining the behavior. It is not telling us where how this should be implemented, or where the sorting should happen, or if we should sort at all. We could, of course, always iterate the whole vector and just select out the minimal t value, which is greater than 0 or something like that. But I guess sorting would be a nice thing here. So is there actually, does a vector, we have it open here, has it something like sort? Let me just check. I guess there will be something implemented for that. Sorted, subslice, sorted what? Sorted, binary search. Okay, we can do a binary search. That's nice. The comparator function should implement the sort order. Okay, but we don't want to binary search something. We want to... Yeah, okay, I guess we can do this. We can just reuse the partial comparison. Then here we can essentially more or less do it like this. Okay, so let's check. And I guess I want to do this on the data given directly. So I think I want this to be mutable here, so that we are clear about this. And then I guess we can simply, let me put this in here, and we say this is now our intersections, and we want to instable sort them by this closure here, and we are going to do, it's in an intersection, so we are actually calling this on the, we are calling this by sorting the t values. So mismatch types expected reference, but Okay, so the partial compare is expecting a reference. Yeah, okay, seems so. So okay, let's format this. He wants to do it in one line. So yeah, I guess now our values should be sorted. So the hit functions should be quite easily possible to do. Like I guess we are returning the first non-negative one. So yeah, so I guess we would need to do something like for I in or for intersection in in self.data. Okay, then the hit function of course needs a self reference here, self.data iter. So we are iterating this one, and if intersection.t is bigger than 0.0, return intersection, I guess. No, return some intersection, because we have an option enum here. And if we are at the end of this and we have reached the end, we are returning none. And then I guess we don't need this this none anymore. And there's a mismatch type. Expected struct body intersection found reference to body intersection. Yeah, but I guess we can only give out a reference here. So maybe I need to yeah, but I don't want to give out a reference. I want to, so let's dereference this. But mismatch type, expected option found nothing. Where does it get nothing? So it either returns this here, or it should end up here and then return none. So, oh no, there is a, yeah. Okay, cannot move out intersection with this, which is behind a shadow. Yeah, we cannot, because most likely our intersection, where did we store our intersection? I guess it was here somewhere. No, we definitely need to move out this intersection into the... Where did we put this intersection thingy? Intersectable? There it is, intersection. So yeah, let me just quickly move this to the intersections file, because this is where I'm always going to search for it. So yeah, we now of course need to fix some, oh no, we need to fix some imports, I guess. There we go, and now I guess we need to, did we have it before here? Yeah, we are already including those here. Is there something broken here now? There is something broken. Mismatch type, expected intersection, found body intersection. What? So did I just copy it and not move it over, maybe? No, it's not in here anymore, so that's kind of strange. Maybe this is just a leftover. Let's check if this works. So the main problem we had here was that it now cannot move the ownership. Makes sense, I guess. So, but we could easily have this intersection then. Yeah, I guess we will have this intersection then copy and clonable, and then, yeah, then our body needs to implement copy and clone as well. So let's check this out now. Should actually work now. The trait copy may not be implemented for this type. Why not? Clone is not satisfied. The trait std clone is not implemented for body. Okay, but didn't we just tell it that we want to actually implement this here? Maybe we haven't done it for sphere. Yes, we have. So there is, I guess, there is something wrong again with the IDE. I really need to check what is happening there. Why is it? Yeah, now magically everything is correct now, or what? Okay, it's still initializing, so maybe... No, yeah, now it's... Okay, so now we can actually do this, I guess. So now we can sort this, and then we can run through this and return it. And so now actually our hit tests may work. Let's check. Cargo test. Okay, so we still have something wrong there. Let's see. Binary operation cannot be applied to intersection. Yeah, because I guess we didn't implement partial equality for our intersection. So maybe let's just derive this one. Partial equality should be possible. So now let's test this again. Okay, 2 warnings, but the tests are running. So are those tests really running? Intersections. Yeah, okay, so those tests are running. That is nice. So then let's go ahead and check what those warnings were. We have an unused create f in body. So yeah, then let's remove this. And this is the same warning. So let's just do a cargo test, I guess, again. Yeah, okay, so let's maybe do cargo build. It builds. So everything is still working out fine. And so as we have now implemented our hit function, I guess we have everything in place to do our first ray tracing. We should be able to now send rays through the scene and check where they are intersecting with the sphere. But let me check if we have really implemented everything now, which is in this chapter, and we can go ahead and maybe put everything together. Yeah, so I guess let's clean up this editor first for a little bit. So we don't need this anymore. This was the preparation. We have now implemented all of those. The tests are running. We don't need this sphere anymore, this rays anymore. Let's close the right side altogether. So we have our lib here, fuzzy equality, intersections. Yeah, do we want to structure things somehow differently? No, I don't think so. Let's remove this new line there, which shouldn't be there actually. We have our tests in here. We have now our intersection as well as our intersections collection simply in this intersections file. I like that. We have this body implementation, which actually has this intersectable trait there as well, which is, I guess, quite fine because so we have everything in one file we need to append information to once we are at the point where we want to implement more methods inside this trait, or we want to implement more different body types to then dispatch this correctly. So I guess this is okay as well. Matrix we did only open to have a reference on how we actually implemented this indexing stuff. So there's the sphere. We have implemented our sphere struct, which has the transformation matrix, which has implements intersectable, yeah, and is therefore an intersectable object, which is quite nice, I guess. And we have our ray implementation, which can be transformed and which can actually be moved along and calculated with a specific t. Yeah, that's okay, I guess, as well. Yeah, so I guess we are ready to complete all this. So let's do this. Let's push this. And yeah, by the way, I've installed a cargo crate with cargo, a crate called Husky crate, I guess, or Rust Husky. Or let me quickly check the cargo toml file, how it's called. Cargo Husky. It's a dependency I actually knew from Node.js projects I'm working on. It's the re-implementation of a service called Husky, which allows to easily install something like pre-push hooks, for example, for Git, which you have seen just here in action. Once I call git push, it will automatically run all the tests and ensure that I can't push something with broken tests. And it will do something else, which I learned then as well. There is a tool called Cargo Clippy. We can call it like this as well. And Cargo Clippy simply kind of enforces or lints our files and gives us a hints about best practices in Rust. For example, if we are doing something like, let's give you an example here, like, where is it? The sphere. Intersections, for example. In this case here, not in the tests here. For example, if I would have done a return here, it would have been perfectly fine with the compiler. There are no compile problems at all. But, so let me show you. If I do a cargo test, it's perfectly fine. It's running. There are no problems compiling this, and this is valid syntax. But if I call cargo Clippy, the default configuration of Clippy tells us this return is completely not needed here. This one is actually needed because we need to tell the system that we want to return something here explicitly. There it is okay because we are inside the loop and we want to kind of jump out of there and return something prematurely. But this is just the end of the function, and there it is preferable to just do this implicit return. And Cargo Clippy kind of gives us hints about best practices or the suggested default Rust linting and file best practices. So it will complain about something like this. You can configure it, of course. I could change this rule and say, no, I want this for my project, but as I have no idea yet what is good and what is bad, I've just left it on the default configuration and it works quite fine. It actually complained about some things which I just then fixed. It was mostly something like explicit returns I used, where those implicit ones are preferred. But I've integrated this one into the Git push checks as well. So this is working out quite nicely as well. So now that we have everything available at our fingertips now to actually cast rays into or against a conglomerate of objects, at least against spheres, or for now one sphere, or however we want to do this. We could actually have those intersection calculations, cast rays through the scene, and then see where they hit and where they don't hit, and create the first ray-traced output, I guess. And this is essentially what the book tells us to do next. Like we are simply having one sphere in the middle of the screen, and we are firing rays through it and checking if we hit it or not, and then kind of printing the silhouette of a sphere. We don't have implemented lighting or stuff like that yet. We will do this in the next chapter, but actually we could ray trace something within the scene now. And this is exactly what we are going to do now. So let me create a new file here, as we have done always before. Let's call it chapter05.rs, and there we are. So I guess before we can start implementing, we need to talk about what we are actually going to implement. So let me switch to my drawing board here and let me show you what the book now tells us more or less to do. So what we are going to do is we have some sort of object within our scene here, which is our sphere. I know it's not a really nice sphere, so let's try this again. Okay, I just can't do it better, but it's not a problem, I guess. And somewhere we have actually our canvas. Can I draw this perspectively? Let me try. So we have something
how would it need to be? Something like this, I guess. So we have this canvas here, and now we somehow want this one to end up here on this canvas then in the as a result. So we want to kind of project this onto our canvas. But how are we going to do this? We are going to do this using race, of course. And this is by we are choosing some point, for example here, and then we are firing lots of rays into our canvas, and each of those rays will either intersect the canvas, the sphere, or it will not. So if it intersects this sphere, we need to project this according to the canvas, and if it doesn't, we simply don't. So what we can do now is you can actually you can think of that is the example the book uses. You can think of this point here like a flashlight which casts its light rays to the sphere, and everywhere it intersects actually with it. It kind of casts a shadow on the canvas, and where it doesn't intersect, it doesn't cast a shadow. So what we are actually doing is we are tracing this shadow. So we have this origin here, kind of, where we start. We could call this origin or camera position or whatever. That is essentially our position where we are starting to fire our rays. We have the canvas essentially, and then we have our sphere, which we are going to project onto the canvas. So let's see how this works out in the end. So, and how we can implement this. So let me just put away my tablet here again, and let's take a look on how to actually implement this. So the first thing we need for this is, of course, we need to start by creating our main function here. So this is already working out. So what we now need is, I guess, let's import a few things we need. So we will need, or let's just start writing, and then we will import them as we are going along. So the first thing is our origin we are going to need. So that is what I had in this diagram, the origin point where all our rays originate from. So let's define this. Let's call it ray origin maybe. It will be a tuple. It will of course be a point, and yeah, let's for now position it at 0, 0, 0, and then just talk about it in a second where we will put this. Okay, why can I now not tell it to include the tuple? Is it not going to build this? Do I need to? Let me just quickly check. Cargo run bin chapter 05. Maybe I need to compile it first once, and then it will. Yeah, it is not finding this one, but my IDE is again not seeing this. There is something really strange. Maybe I need to reconfigure this, or okay, this is it's just not detecting. Okay, it's okay, now it's working. So let's import this. So I want to, how did I actually do this in the other chapters? I guess okay, maybe this is the problem. I need to define this one here, or I could actually import it by full name. I guess it doesn't make a really great difference. So yeah, but the question here is, where should the point be? Because if you look at this image here, you can actually see that this origin point, we defined this sphere is at the center of our world. So essentially, let me just quickly point this here. There is somewhere there is our 0, 0, 0 coordinate. So obviously the origin is not at the 0, 0, 0 position. So let's move it. For example, back by -5 on the z-axis. So actually back from us, which is quite reasonable if you look at this and you in your head you rotate it by 90 degrees. This is essentially the perspective we are wanting to achieve. So let's move it back there. And then we need something like we need the position of the of our canvas. So we need the position of this here, this thing here, this canvas. We need the position of it. So where is this one positioned? We need to think about this. Let's call this thing wall for now, or we could call it maybe canvas. Yeah, I guess canvas position. Why not? Let's call it canvas position Z. Because we are positioning on the z-axis there, as we have done here, and the canvas should be behind the sphere then. So let's position this one. It will be, do we want to use a tuple? No, we have this z position separately. So where should we position it? Let's position it maybe at 5 behind the sphere, so just into the other direction. Let's just try this, and then we would need what do we need as well? What have we done now? We have the positions of those objects. We need, oh yeah, we need the size of this thing. So let canvas size maybe. And for now, let's assume it's a square. It's not a rectangle, but it's square. So this makes things easier. So let's maybe say, okay, we have a wall which is 10 by 10. Okay. And now, oh, I called it canvas there. And now what we actually need to do is we need to define. So now we have defined this in this world space here, in this space, in this three-dimensional world space. So we have here this origin point. We have the sphere, which is of course it's of course a sphere which has a radius of 1. But we don't actually have transferred it over into our two-dimensional canvas result, which we want later on. Like, let me remove this here again. So we have this canvas size of 10 there, but this is within our virtual three-dimensional space. We need to somehow transfer it to a real canvas later on, the canvas implementation we have with all the pixels and colors and stuff like that. And I guess what we want to do is we want to project this to a specific value there then. So yeah, we should just choose one, I guess. But then I'm now questioning the naming here. Because essentially our canvas will be, the book calls this thing wall, and maybe we should too. Let's call it wall then, wall size, and then let's just have now a canvas size. This will then be our real canvas, and let's maybe have it 512 pixels, and this is a real integer now and not a floating point, because we can't have half pixels. Doesn't make sense. We can't have a color for half a pixel. So yeah, let's maybe define this, and then actually we need the canvas itself. So let's create a canvas here, and we need it mutable, of course, because we will put colors on it. So I've set it as square, so it will be canvas size by canvas size, I guess. So now we have this one, and yeah, of course now we need a sphere to cast, which would be sphere new, I guess. And we said we wanted in the, we need of course to require all of this, and we can actually, yeah, maybe we will just, yeah, let's just use the full naming here actually, because why not? So because then this makes things easier. So the sphere, yeah, it took a transformation matrix, but we could supply none as well. So now we have our sphere at the center of everything. So yeah, I guess now we need to cast our rays, and we need to cast our rays for each of our pixels. We might need further information here, but we will see this once we start implementing it. So I guess let's start to implement this. We will have two loops, of course, because we need to loop for the x and the y coordinate through our canvas. So I guess we will do this by, for x in 0 to canvas size, and for y in canvas size. And as I actually like to scan a picture row by row, because I find it more easily accessible in my head than scanning it column by column, I will actually put the for y outside of the for x. So just let me put this there and reformat it. So yeah. So what we have now is we need an array which is originating at our starting point, at our ray origin, for each of those pixels, then going through the scene to the essential yeah, to the representation on our virtual wall. So essentially here, the representation here, starting from our origin, we now need for each of those pixels here, this there will be a pixel on our wall. We need each ray going through the scene and check if it is intersecting with the sphere or not, and doing stuff based upon this information. So as we need this, let's see how we can achieve this. Our wall here is in world coordinate space, but we need to calculate it for each pixel of our later on target canvas. Our canvas could be arbitrarily large. This would, however, not change our world scene. It would only change our resulting image, our kind of information density inside our canvas, our image, how big it is and how precise it is in the end. So what we need to do is we need to calculate the representation of the position on our wall based on this canvas size. So what we need to do for this is we need to actually calculate what such one pixel of our canvas is in world wall value, more or less. So I guess we will do this, and let's call this maybe canvas pixel world size. And it should essentially be not that hard to calculate this, because we have this here and we have our wall size, and essentially it is then just our wall size divided by our canvas size, because both are square, which is nice to calculate. And so if we have the part of how many of those pixels are here, we should get a floating point which provides that. And now we have cannot divide float by, oh, okay, yeah, cannot divide float by integers. So maybe we can just convert this integer into a float, I guess. Okay, so now it doesn't know what to cast it into. So can we do no, f, we called it from. And of course, then we need to get our f here. Type alias is a private type alias. Oh, didn't I? Oh, I did not. So, oh, that's interesting. Yeah, so maybe I don't need this here. I'm just using an F64 hard-coded, because why not? So okay, this does not work. It's not satisfied by the trait convert. It's implemented for trait bound. Standard convert from usize is not satisfied. So we cannot convert this. Can I just tell it to use it as an F64? Is this going to work? Yeah, this seems to work. So now that we have our canvas pixel world size there, we should actually be able to let's see. We should actually be able to create our ray, shouldn't we? So now we are creating a ray, which is a new ray, which has the origin point, which is our ray origin always. And it should go into a direction which points from our origin to the target point on our wall. So let's calculate this here. Let's call it wall point, maybe? Yeah. And wall point should be a tuple, which is a point. And this one lies, where did we position our wall? We have this wall Z position, so I guess let's define those two later. I guess the Z position there is then our wall position Z of course. And now our X and Y are corresponding to the position with regards to our real world X and Y, and we need to calculate this. So let's actually, yeah, let's call them let's call them world X, I guess, and world Y for now, and let's just have them here, world X. Let's just set them to 0, 0, just so that the compiler isn't complaining. We will check this in a second. So how we calculate this point? Let's think about this in a second. Let's now create this ray. We would have to go from the origin and in the direction to the target. So to this wall point. So what we need to do, I guess, is then here create a new result from our wall point. Yeah, exactly. So if we now subtract our wall point from our ray origin, we are getting a vector which points from our ray origin to our wall point. That is exactly what we want. And we will normalize it here just to ensure it has a proper length of 1 so that we can easily step along it and not have any problems there. So this should actually be our ray then. Undeclared type ray. Yeah, I guess we haven't imported it then. So now that we have this ray, as I've said, let me put a to do here. To do, calculate the correct values for this. Let's do this later on. Let's just assume now we have this for every for every x and y. And so we have our array now. So essentially now we could just fire our array into the scene, and we do this by telling the sphere to intersect with our array. And let's store the information here, intersections, and method intersect not found for sphere. Why not? Wait a second, didn't we? Intersectable, intersect. That's kind of strange. Do we need to? Oh, I guess we need to import this trait, don't we? So use, let's just copy it. Oops, let's just copy this there. And I guess we had this trait in the intersect. No, in the body body namespace, I guess. Yes. Now it knows how to intersect with array. So that's quite nice. So now we should have intersections there. And yeah, I guess let's check if there are intersections. So we implemented our hit method. So we can do if hit, if xs hit, and we don't need those there, is not none, I guess. Is not none. We want to do something, and what we want to do is essentially tell our canvas to write a pixel. Was it write pixel? It was write pixel. Okay, so then let's do this. At the x and y position, we are looping here because we are looping in our canvas coordinates here. And oh yeah, we need a color. Oh, yeah, so I guess let's somewhere here define a color new 1.0, 1.0, 0.0, just because yellow is my favorite color. So I guess let's let's call it yellow, and let's call this one yellow as well. So as I've said, we are not doing any lighting here or something like this. So we just want to check and project this silhouette. This, you remember the flashlight example. We just want to project this silhouette onto our canvas and check what's the result of this. So I guess we are then writing this there, just in the coordinate space, and putting it in there. Yeah, that should actually do what we want. We are putting the color yellow there. Let's format this. Okay. So if we have a hit, then we are writing the pixel. Yeah. And if we are not, hitting anything, we don't need to do anything because our canvas is initialized with black, I guess. So this should actually give us the silhouette. So essentially this should work. This should project our silhouette. Even though I'm not 100% sure this values here, this distances and so are correct to in the end see something of this sphere. We will then play around with this, but this should work if we finish this up. So let's think about this for a second. What we are going to do here is we need the let's think about this. So we have let me get this tablet in front of me again. So we have somewhere our, maybe let's just zoom in here a little and draw it here. we have our canvas here. So this is our no, not our canvas, our what did we call it, wall, this thing here, this one, the thing in the three-dimensional space. So this one we have here, and we now want to, this is actually, what was it, let's see, we had it wall size, which is 10. So this is 10 by 10 in world space, and we now need it in canvas space. Canvas space, let me do this here, was 5 it was 512 by, oops, damn, 512 by 512. So the first one is world space, the other one is canvas space. So now in order to calculate this position, we have the aspect of this. So we know with this value called canvas pixel world size, what's the fraction of this calculation, wall size divided by canvas size. So in order to get the proper position from our x in, let's say we have an xy here somewhere, it's this point for example, it should essentially be as easy as multiplying the x value we have should multiplied yeah, come on, should be multiplied with this what is it, 10 by 512, and this should give us the x position in our world space, shouldn't it? But we have a slight problem there. The problem there is that this is not quite right, because this assumes that the origins of our spaces are identical. Currently it is the canvas origin is here. That is the origin in our canvas. But where is essentially the origin of our world space? You could assume it is in the bottom left corner, but it isn't. Because if you look at this picture, our sphere origin, yeah, this one there, let me just get something like red. It is here, it is in the middle. And this actually projects to the middle of this canvas. So we need to take this into account, don't we? This implies that our canvas is, the origin of our canvas is, of our wall is actually here. So we need to, in order to now convert this x values we got from the canvas, which we are iterating through, to the world values, we actually need something like, we need to, if we want the world value for, let's say we have, let's make it easy, and let's say we want to convert 0, 0 in canvas space. This would actually be, wouldn't it? It would go there and then up there from our usual origin. So it would be minus 5, wouldn't it? Because we have a size of 10. So it would actually be minus the half in one direction and minus the half in the other direction. So, oh no, sorry. This is not right, is it? Because this direction here up is not minus, it's positive. So actually it would be it would be minus 5, wouldn't it? Yeah, it would be. It would be minus 5 in the x to the left and 5 up, because y is going up there. So essentially what we need to do here is we need to go ahead and have some formula for this, and we can easily derive this. So assuming this 5 is always half the size, let's maybe call it half. It would be quite easy, because once we are moving along the x-axis, it will be minus half always plus x, because x is just going along here in our, or let me color this correctly. It would be plus, it would be plus x in this canvas space. So minus half of the wall space plus x from this canvas space will be the real x then. And in this case, half, so the y up minus the y from the canvas space, should actually be the correct position then in the world space of the wall, because we need to subtract this, because we are moving down with each row y we are going further along. So this should actually work out well, because once we are below this middle point, we are here going into minus y territory where it gets negative. So this should actually work. However, of course, those x and y values here need to be multiplied by the correct value to have it like 10 512 and 10 512, so that we have this in the correct coordinate space. So yeah, so let's actually try and implement this. Let me put back this tablet again. There we go. And now let's see. So what did we just say? We said we needed this. Oh, we needed this half value, don't we? So let's define it. Half is, what's it? It was the wall size divided by 2 then, I guess. This is half. So now we have, what did we say? Minus half for x plus the canvas space x multiplied by this canvas pixel world size. So canvas pixel world size cannot multiply a U size by F64. So yeah, I guess we need to convert this into an F64 then. Maybe put brackets there. They don't seem to be necessary, but yeah, you never know. So now let's do more or less the same thing for y, but we said, let's check. We want the half minus. So half minus, of course, y now, and multiplied by the canvas pixel world size. So yeah, this actually looks okay to me now. So let's check if this works out. I don't know. So yeah, maybe we should then write out, as we did before, the created ray traced canvas here to a file, I guess. So how did we do this actually before? Let me copy this code here. So let me put this here, and oh yeah, we need to get all those traits and stuff. Yeah, let's check what we needed to implement to have this write here. It comes from stdfs write. So yeah, let's import this as well, I guess, and maybe we will just import everything from canvas here, and instead of all those different thingies here. And I guess I will do this with everything we needed here, because I just think it will be cleaner. The canvas challenge current scope method. Okay, did I do something wrong here? Oh, I guess this should actually work, shouldn't it? Maybe it's just the IDE again. So let's try and build this. Okay, so seems to be something really wrong. The method is available for canvas canvas here. So did we actually have this somewhere else? Oh, yes. So I guess I need to import this separately because we have it in the 2ppm module and we have it in the 2png module. So now it should be okay. And now before we start ray tracing, let's just, because I guess 500 by 512 by 512 ray tracing pixels, this is actually, it is quite an amount of pixels. So let's just, it might take a while. So let's just put out some information here like ray tracing something pixels. Please be patient. And the number of pixels actually is the canvas size power 2. So let's print this out. Okay, there is no power. So, oh, is this not defined on... Oh, it's just pow then on integers. Yeah, it makes sense because we actually can have a power of and then a floating point with an integer. Okay, that makes sense. So yeah, let's kind of try this, I guess. Cargo run -- bin chapter 05 and let's... Okay, it's ray tracing 262,144 pixels and it was quite fast. So let's see if it rendered something. Let's see. There is an output. Yes, yeah. We actually we did our first ray tracing. We ray traced a sphere. The silhouette of a sphere. Okay, it doesn't look like a three-dimensional sphere yet because we have no lighting and stuff, but we actually fired rays into the scene and got out our first ray tracing result. We fired the rays and we projected this sphere to the canvas, which is actually really, really nice. And now, wait a second, where did it go? There it is. And now, this one here, as you can see, has quite jagged edges. This is because I'm now, of course, scaling it up. It is firing those amount of pixels into the scene, like it is 512 by 512, and it can only be as precise as we have for this amount of rays. We will see techniques later on to have more precise matching there and doing some sort of anti-aliasing and super sampling maybe and stuff like this. I'm not even sure if the book is talking about this, but I guess maybe if I have as much fun with it in the future than I am having now, I will implement all of this in the future as well. But for now, I guess we can simply cast more rays into the scene by maybe not doing 512 here, but 1024 and see what happens then. It will take a lot longer because now we are exponentially growing our pixel space, but let's see. So now we have, as you can see, over 1 million pixels. That's something more to go by. So as you have guessed, it takes a lot longer. And now, yeah, of course, writing the ppm does take a lot longer as well. But now let's see, we should have, yeah, and as you can see, we have a result here, and the output of this result is clearer because we cast more rays into the scene and we don't have all these artifacts here now. And we could even go even further, and let me put a time in front of here to see how much time it took, and let's do something really crazy like 4096 pixels in canvas size, and let's just render this, which is what is it, 16 million pixels now, or 16 million rays which need to be cast and intersected and calculated and stuff like that. And we are not even doing something like intersecting this thing or calculating anything like reflection or lightning or any other things which will be calculated later on, and more rays will even be fired off when it hits, like to see if it is illuminated by something or if a light is there shining on it and stuff like that, which will take even longer, of course, because we need to do more math there. And still, as you can see while I'm talking here, it is still rendering, which brings me to, maybe I will check if there is a crate there which allows us to put some sort of simple progress bar in there. If this is simply possible by including something and just telling it to print it out, we could do it, or we could just print out every, I don't know, every 10,000th pixel or something like that. Because this is taking a long time. We could, of course, speed this up in the future, and most likely will, by somehow making this parallel. As the system I'm currently working on here has eight CPU cores to work with to render this, but it's currently only using one. Because we have a completely single-threaded, single process calculation here, and this is why this is taking so long. And I'm not even sure if I should maybe abort this and check then back, but because I have no idea how long this takes. So yeah, I guess I will just let this run here now, and I will then just, through the magic of editing, cut to the moment we have rendered this, and then I will tell you how long it took, because I'm now really intrigued by this myself. So yeah. So through the magic of editing, we will be finished just now. Magic. There we are, and it only took essentially 245 seconds. So yeah, maybe this is not that bad actually, but it took quite some time. But let's see the result. And is this the even correct result here? Is it? Let's see. No, there it is. And as you can see, it is really, really smooth now. There are no visible, not really visible edges here, and essentially this is one technique you can apply later on to make it better, to make the results better you get from your ray tracing. Like, you are just firing more rays into the scene. This would be one technique, just rendering a bigger scene and then shrinking it down, and there is something like super sampling, which is simply for each pixel firing multiple rays into the scene and then combining the results and just offsetting them like a sub-pixel away always. But we will get to do this later on. But for now, we have essentially really rendered our first ray traced image. And this is essentially the magic of ray tracing we did here, which is I really much enjoy, and this is fantastic. So yeah. So let's just check if there is something like a progress bar for Rust, which we could use for the CLI. Progress bar CLI Rust, and I guess we can just then open up the first result directly. Yeah, so this is, what is it? Indicative. Okay, this is a lot more, okay, this is a lot more fancy than I thought we need, but can we, okay, it seems to have, oh, nice. It seems to have all kinds of stuff in there. What is this? Examples, something like this. We only want something like this, would be awesome, just for, so how does this work? We are importing it. Okay, we are creating it, and then we can simply tell it to increase. Okay, so yeah, I guess we would need to do this step by step, but
This looks actually quite nice. How is this called? Indicative. Let's check. Let's just cargo search for this thing here. And yeah, there it is. Let's copy this and let's put this into our cargo toml file here. So we have our second dependency here. Let's do a cargo build then. So for it to be installed, okay, now it's there. And now how was this going to work? There was this example, no, where did I just have it from here? Example single, so we are just using this and then creating this and then, okay, so yeah, so let's try this. Use indicative progress bar, I guess, and then yeah, let's create let progress be a new progress bar with the the canvas size. No, not wall size. Canvas size. Oh, I made a dot there. Canvas size dot to the power of 2. So not working? Why not? Mismatch type U64 found use size. Okay, as U64. This shouldn't be a problem to be converted. So let's do this, and then if I understood this one correctly, we can simply have, after each of those loop thingies, we should be able to tell it to progress inc1. But this will slow as hell now, because now it will, for each rendered pixel, update the CLI. But let's just, so we need to make this better. But so let's just check for a 512 by 512 again. If this works, would be really nice. Cool thing. Yeah, I like that. But as I've said, it's now, we will just time how much it is slower now because for each pixel it needs to update one line to the shell now, which is of course quite slow. So we have now a total here of 16 seconds, I guess, and if I remove this one again, it will be a lot faster, I guess. So we need to somehow, yeah, it's ray tracing and it's writing, and yeah, it's so you can see how much this shell output cost us. So this is not, we don't want to do this for each of the rays, but let's say every 1,000 rays or something like that. But maybe this progress bar thingy has something for this to make our life easier. Okay, that is really nice. Set draw, so we could actually tell it to just redraw once every second, or once or twice every second. Okay, is it really? Okay, let me check if it's really as simple as this. Progress, set draw rate, and then like, for example, 3 times a second. Okay, let's try this. Okay, that is awesome. So now it cost us nearly nothing. Yeah. But it stops too early. So, oh, okay, it doesn't seem to... Is there, because I read something like is finished? Is there something like finish maybe? Oh, there's something like finish. Finish and clear? Finish at current pause? Yeah, finish, I guess. Then can we just call progress.finish here, and then maybe it will look right, and maybe we can bump it up a little bit and tell it to draw 5 times a second or something like this to make it a little bit smoother. Okay, this looks nice. Yeah. Okay, and it didn't really cost us any performance. Okay, that is awesome. So
Let's maybe bump this up to a bigger value then again, 2048 maybe. And yeah, and there you can see it takes a lot longer and for such a huge amount of pixels to be rendered, but still it works quite nicely, I guess. This is nice. I really like this. I really like that there are such crates available which simply work and do what you want. So yeah, I like that. So once this is finished, I'm going to to commit this, I guess, and I guess then we are quite ready there. This is really nice, and it's working out really nice there. So yeah, writing output. Yeah, the ppm writing routines are very slow, and I'm quite sure I know why, because I'm using vectors there, and for each of the values I have, strings, I'm pushing them into a vector, so it's all the time it's resizing this vector and mem copying all of the stuff into a new area, and then it's resizing it again and mem copying it again, and this is very slow, of course, because it's doing it for nearly every pixel value. And we could easily fix this and make it faster, but maybe I will just use my new PNG output for in the new experiments instead of ppm. But yeah, we will see. So yeah, now we have 1 minute for a 2048 by 2048, but before committing, I guess I will make it a 124 per 124 picture, because it is okay and it is nice and it is enough to be shown. So yeah, I guess let's add cargo lock and cargo toml there. Yeah, that is awesome. Let's push this. So the test should run again, and this clippy thing should run again, and yeah, nice. Okay, so now it's pushed, and yeah. So even though I usually end this with the Raytracer challenge book up again, I will end this now with our first raytraced sphere, because I really much enjoy this, even though it's just a yellow circle on the screen. I really much like it that we now have everything together to start really doing some ray tracing. And as I said, the next chapter is about implementing basic lighting. And so then after that, we will actually see a more three-dimensional looking sphere at the screen. And I love that we can then just do that. There will be a lot more to do in order to achieve this goal. We will need some more math behind it, but yeah, I guess we will work through it and we will implement it. And I'm already really looking forward to then doing this with you, and to have another ray traced sphere with lighting then as a result of the next chapter. Maybe not the next session we are doing here, because it is quite some stuff we need to do, but at the end of the next chapter, in maybe 1, 2, or 3 sessions, we will see, we will have a lighted sphere, and this is something I'm really looking forward to. And until then I'm just enjoying this yellow circle, which actually is a 3-dimensional sphere. We just can't really see it, but it is a 3-dimensional sphere. And I'm just enjoying this. And yeah, thank you for joining me and doing this. And I hope I see you the next time. Please subscribe if you want to be notified the time the next video comes up. I'm kind of pledging to do this in a weekly manner, as you have may have noticed before. I hope that I can keep up with it and publish one video every week. It's even though I'm more or less just recording my sessions here, it still is a lot of work. Like, I need to somehow cut scenes out or speed them up, as you have seen in the video before. When I'm learning and scrolling through pages and just thinking about stuff, I'm usually doing like it, like having it 2 times the speed, or even faster, like a fast forward. And then I need to cut this right, to do this right, and then I have to upload it, and yeah, it's kind of some work. I need to prepare the tests, as I have done in the last 2 sessions, because I like that, and it gives it more speed when we are going along. And yeah, it's quite some work, but I hope I can keep up with a release once every week, and so I'm already looking forward to the next one. And yeah, stay with me, subscribe to the channel if you like it, give me a thumbs up if you like this kind of videos, and yeah, if you have any questions or remarks about this, please feel free to comment below, and yeah, I see you next time. Bye!